Okay, welcome to Transportation Engineering. Today we are going to start on Module 2, which is basically highway geometric design. First, we are going to start with the highway functional classification. To understand the concepts of functional classifications, highways are basically classified according to its functionality. In most trips, if you go from one origin to another destination, you start from your home, you get to an access road, to a collector, then you go to the main road, then you move, when you approach close to the destination, you start shifting from the main road to another distributor to another access road. We can divide most trips into main movement, transition, distribution, collection, access, and terminal. That means if you are in this origin, for example, that's your origin. So you need to have access to the network. That's the road in front of your home. Then you go from that road to a collector, main street. Then this main, so that's the access. You go from the access to the collection. So that's the collection. Okay. Then from that collector, you go to access a highway. So this is transition. Then you go on the highway for a long trip. That's the main movement. Then back, when you approach your destination, you exit from the highway through a transition. And from the transition, you go to a distributor. Then from the distributor, you go to the terminal, or the last segment of the trip. That's what we mean with the functional classification. That's why in freeways you'll find a lot of traffic, but in the street in front of your home, if you count the number of vehicles passing per day, just a few hundred vehicles passing per day, or less than that even. It depends on your neighborhood. So that's of course when we are designing a main movement highway, our consideration for design will be different than designing an access road or in a neighborhood or something like that. So as we can see here, for the main movement and the transitions, those are usually freeways and highways. Their characteristics: high speed, and also there is limited accessibility. That means you can access, for example, King Fahd freeway, you can access it through ramps. You cannot access from any point on the to the highway, on the road. Then there is the distribution and collection. For example, we can take an example here in Khobar, the Khalid ibn Walid, for example. Okay, it has a moderate speed. It's not as high speed as King Fahd. It has a moderate accessibility. Okay, so that's arterials and collectors. When we go to access and termination, you will find that it's local streets primarily, and it must be low speed. It's neighborhood streets, and it has a high accessibility. So from this we can make this classification. That's the higher the rank of the road, arterials, highways, freeway, mobility is high, speed is high, and this the accessibility is low. In the middle, there is the collectors. So there is sort of a balance between mobility and accessibility. For local streets, accessibility is high. You can access from any point. but the mobility, which is basically speed, okay, in local streets are very low, okay? So we can, this is primary, or that's the what we mean with the functional classification. And also the functional classification play a major role in the geometric design of the highway. So here, based on the previous example, the following conclusion: traffic volume is at its highest at the top of the classification, okay? And of course, the volume here is maximum, okay? So the volume is at highest at the top of the classification. At the top of the classification, mobility is very high, but access is limited, okay? At the lowest in the classification, access is very high and mobility is very low. Any question? Okay. So now, before we starting on on design, we need to understand the design controls and the design criteria. So first of all, similar to structural engineering, what is the design load and what is the planning horizon for us? So this is the projection of future traffic demand. Okay, so this varies by facility. This component or this element in designing highway, it varies by facility. For example, if we are talking about right of way, okay, we plan for life expectancy of 100 years. Minor drainage and base course, that's the structural layers of the highway, we look for 50 years. Bridges, okay, the planning horizon between 25 to 100 years, and actually we tend to use the 100 years. So, for example, I'm not talking about the structural design, I'm talking about the geometric design. So if you want to identify how many lanes we need in a bridge, we plan for more than 25 years, because bridges are not the structure that you build every 5 years or every 10 years. Pavement resurfacing, that's in maintenance, okay? Every 10 years. Pavement structure, when we design the structure of the pavement, we use at least between 20 to 30 years. Pavement reconstruction, from 5 to 10 years, and so on. Here, the right of way, this is basically when we acquire right of way, okay, we look for 100 years. The second, which is basically the speed. What speed we design the highway for? So speed is a key design control for highway geometric design. Why it is key design? Say the speed is the key design control for highway geometric design. Why? First of all, it defines key design elements in the highway, such as horizontal and vertical curves. Okay. It plays a key role in determining lane capacity and highway facilities in general. Speed is a key factor in functional classification of highways. So these are the three main elements for why speed is a key design control for highway geometric in highway geometric design. Regarding speed, we have different types of speed. We have operating speed and we have design speed. So what is the definition of operating speed? It's defined as the speed at which drivers are observed operating their vehicles during free flow condition. Okay, so if you take a sample and conduct a speed study, that would be the 85th percentile speed. That's the 85th of observed spot speed sample. Can be considered as the operating speed. The design speed is a selected speed value that is used to determine various geometric design features of the highway. Okay, the design speed must be logical with respect to topography, adjacent land use, and the anticipated operating speed, the functional classification of the highway. For example, you cannot design, for example, a highway in the desert, okay, and there's empty land on both sides of the road, and you select the design speed to be, for example, 80 kilometers per hour. Why? There is no, justification for that. That's number one. So you are not anticipating such a speed in that, location. Also, it's a freeway or a highway. So regarding functional classification, this is not anticipated. Okay, unless we are talking about topography, for example. If you are talking about mountainous road and you reduce the speed in a certain segment to 80 kilometers per hour due to topography, that's expected. But that's what I'm saying. That selecting the design speed, it must be logical with respect to the following: topography, anticipated operating speed, adjacent land use, functional classification of the highway. Again, how we select the design speed. So it says that design speed should be selected as high as possible, but we need to give a special consideration for the following: the desired degree of safety, the mobility, efficiency. Okay, so actually desired degree of safety usually contradict with mobility. Okay, mobility require high speed. The desired degree of safety requires low speed. Efficiency, okay, it desires high speed. So the selected design speed should be consistent with the speed drivers are likely to expect on a given facility. This is a very important, design speed should be consistent with the speed drivers are likely to expect on a given facility. Any questions so far? So as we mentioned now, the design speed should be selected such that it gives us the desired degree of safety and mobility and efficiency. So these are recommended ranges for design speeds. For example, for rural freeways and expressway and other arterial highways, it's 120 kilometers per hour. For suburban freeways, 100. For suburban elevated or suppressed freeways, from 80 to 110. Urban arterial between 50 and 100 kilometers per hour speed. That's for urban arterials. There is another design criteria also, which is the level of service. So the guidelines for selecting selection of design level of service, okay, for freeway on a rural level, it's B, okay, rural rolling, depending on the topology of the terrain, depending on the for level terrain, rolling terrain, mountainous, urban and suburban. So these are different values. And as you can see, for mountainous, we are allowing, a C. We are going below the B. For arterial, B, B, C, C. For collector, C, C, D, D. For local streets, it's all the way D. So some of you might be wondering, why, doctor, we are allowing to design at D, or for example, for a collector to be designed at D or C? Why we design? Why we don't why we won't design it for A level, for example. Okay, so to explain this to you, let's go back and to see what are we designing for. We are designing for the projected future demand. So we are designing for, if we are designing for a freeway, for example, okay, we're designing maybe for 30 years from now or 25 years. So that means the design volume you are designing for and that level of service will occur at the design year, at 20 years later. That means when you open the highway now, after construction, it will be operating at P. But when the traffic demand start growing, okay, and so, you know, this means it will be D 20 years later and during the peak hour. So that means when this collector opens today, is going to be operating at A. Okay, clear? So again, our primarily design criteria are the following: the projection of the design year or the planning horizon, you know, how many years from now we are calculating our traffic demand, and the design speed, okay, and the level of service or target level of service for the facility we are designing. Any questions so far? Okay. So now we are going to start with the first component, which is basically the horizontal alignment of the highway. What is the horizontal alignment? Basically, the highway is consistent, you know, on the horizontal level, it consists of, you know, group of segments like this, and these segments are connected by curves. This is what we call horizontal alignment. Okay, so the horizontal alignment consists of tangents, straight segments connected by horizontal curves. So the horizontal curves, this is one key element in the horizontal alignment. How we select these tangents? Usually we select these tangents, okay, based on, you know, either we have a traffic, you know, a water stream or geographic boundary between two sides. If we have a property line between two ownerships, okay. So this is how we try to select these tangents, okay. Then we go to the, you know, connecting these tangents together with curves. So what type of horizontal curves we have? We have either simple curve between two tangents or compound curve. The compound curve, it's connecting between two tangents, but it has two radius. So we have radius 1 and radius 2. There's a reverse curve, okay? This is going like an S shape like this. And we try to avoid this one. But sometimes in mountainous area, okay, we cannot avoid it, okay? And there's a spiral curve. This spiral curve, it starts from an infinity radius, then it goes to the main radius of the curve, then again it goes to you know, infinity. So it's kind of a spiral. It's not circular like this. And this type of curves is not common on freeways. It's very common on railways. And I will explain why later. So before we start on the horizontal curves, we need to just to revise a few elements. This is the horizontal curve. We have, it has a radius, it has a deflection angle, delta, okay? And the delta here is equal to this angle of the curve here. at delta over 2, okay, this line will be perpendicular to the chord line. This is what we call chord line. Okay, this is chord line, and this is M, that's the middle ordinate, and this is the external distance. This is the point of intersection between the two tangents. This is the point of intersection. Okay, and this area, this length, is basically the tangential distance. Okay, and this angle is delta over 2. Then we have L, that's the length of the curve. This is the distance. So this is L, and the chord length from here to here, this is LC. Okay, chord length. Any questions so far? Okay, T, it's basically very simple, geometric functions that we can use. So here, look at the T. This is R, and this is T, and this is delta over 2. So of course, delta tan delta over 2 equal what? T over R. That means tangent equal R tan delta over 2. The M, that's the middle ordinate. Okay, M, we can calculate it very simple. Let's calculate this distance. This distance, and subtract it from R. That means, let me draw this here. So this distance is R, and this distance also is R. Here, this part, this is M. That's the middle ordinate. And this is delta over 2. So M equal R minus R cosine delta over 2. That means M equal R, okay, multiply 1 minus cosine delta over 2. So that's M. E, we can calculate it similarly, and you will get this equation. Any questions so far? Okay. There is another value which we call the degree of curvature, D. Okay, so the D is the value corresponding to an arc length of 30 meters. Okay, so that's D, and that's 30 meters, and this is R. So basically, it's 1719 divided by R. This gives us, okay, the D. Usually, it's derived from the imperial units, which was here 100 feet, and this is R, and this is D. So D basically equal the 100 feet divided by R. Okay. Any questions so far? Also, here R should be in a feet, and we convert this value into degrees. So in order this way, you get d in radians. So if we want to get it in degrees, we must multiply it by 180 divided by pi. And the same here. If you look at it, how we came up with this value. Okay, this value came this way. It's basically 30 divided by r multiply 180 divided by pi. How much you get? Can someone calculate this, make this simple calculation, please?
1718.8.
17,
1718.87.
18.8 divided by r. So we can say it's 1719 divided by r. And r here must be in meters. Okay? So if you have a degree of curvature, you can calculate r. r equal how much? 1719 divided by d. And d should be in degrees. And here going to be in meters. Okay, actually this is an indication for the degree of severity of the curve. Any questions so far? Okay, so what is the design formula for the horizontal curve? Okay, it's basically v square over gr plus 0.01 e plus fl, and fl, that's the lateral friction, as we mentioned before in the beginning of the course, for the criteria or the turning characteristics of vehicles. And actually I'm gonna explain to you how this form, or where this formula came from. Let's just imagine we have a horizontal curve like this, and we have a vehicle here, and it's turning around a radius r, and it's driving at a speed v. So basically, this car has a mass. So there is a force exerted here. There's a centrifugal force, which is basically the mass times the acceleration. The acceleration is v squared over how much? Over r. That's the turning acceleration. So if we look at this vehicle, take a cross section and have a look elevation, we can see that the road, usually in horizontal curves, we make this super elevation. There is a slope in the pavement like this, and this slope is usually measured. This is alpha, and this alpha usually measured as 100, and there is E. Okay, that's the super elevation. So this car will be driving on the road this way, and it has a weight at the CG. So its weight acting downwards, weight equal mass times G, and there is a centrifugal force acting this way, mass times V square over R. Clear? Are
Yes.
these all the forces acting?
You have friction also.
We have reaction perpendicular to the surface, okay, and we have horizontal friction like this, okay. So the horizontal friction is the reaction, okay, I'm gonna say it Fy, and there is Fx, okay, the fx equal how much? Let me just clear this. Okay. Okay, draw. So the x force equal basically Fy multiply, okay, how much? Multiply coefficient of friction, Fl, and that's the side friction. So basically, in order to solve this example, we need to have this ruler and we need to do our analysis on axes that are orthogonal to this. So we have here, okay, this will be direction x dash, this will be y dash, and this will be minus x dash, this will be minus y dash. So let's go back. Just I'm going to change the color and put it blue. So here, if we analyze this centrifugal force, we are going to have a force here. It's basically mv square over r cosine alpha. And here we have another force, which is basically mv square over r sine alpha. For the weight, we're going to have another component here, which is basically w cosine alpha. And here, because this angle is going to be alpha, this angle is alpha. And here will be w sine alpha. And we have the fx, or the let's call it rx actually. And this is ry. So if we go to the basic equilibrium equations, we have summation of fx equals 0, summation of fy equals 0. So summation of fy, we can get to that we have w cosine, and going up is positive, here going this way is positive. W cosine alpha is going to be negative, okay, minus mv square over r sine alpha, okay, plus ry, the reaction in direction 1. This should equal 0. So that means ry equals, let's release this and just so make it m g cosine alpha plus mv square divided by r, and here is sine alpha. For sigma fx, and this direction is positive, we have the following. We have mv square over r cosine alpha minus mg, which is w actually, sine alpha, okay, minus the friction force here, Rx, which is basically Ry multiplied by F lateral. So if we substitute for Ry here, okay, and this should equal to 0, okay? So if we substitute for Ry in this equation, okay, we get the following. We can get, okay, let's take this this part on one side and the negative part on the other side. So we have here mv square over r cosine alpha equal mg sine alpha plus, instead of ry, we're going to put this mg cosine alpha multiplied by fl plus mv square over r sine alpha multiplied by fl. If we divide both sides by m, so m is eliminated, okay? If we divide by cosine alpha, so alpha cosines here are eliminated, so this is cosine alpha, so this means it's tan alpha divided by cosine alpha goes, here goes to tan alpha. So to put this form in a cleaner way, in a cleaner shape, so it's v square over r equals, let's divide it also by g. So the g gets eliminated, g gets eliminated, and here we have g. So it's v square over gr equals tan alpha. Tan alpha is how much? Okay, we define the slope of alpha by E, which is called super elevation. So here it's 0.01 E. Okay, so this is tan alpha plus FL, that's the side friction, okay, plus V square over GR multiplied by tan alpha. Tan alpha here is E, is 0.01 E multiplied by FL. Usually the E we're talking about from 2% to 8%. And the friction here, or the side friction, is, you know, around 0.1 to 0.3 or 0.2 at most for designing horizontal curves like this. So this term, when we solve it, it's very low. So we can ignore it. So we end up only with these terms. So it becomes v square over gr equal 0.01 E plus FL, which is the factor, the coefficient of friction for side friction. Any questions so far? So that's how we got this form. This formula came this way. Okay. Any questions, Shabab? Okay. As I mentioned before, the maximum super elevation is between 4% to 12%. Okay. But, you know, practically speaking, from construction perspective, it's difficult to build or to achieve the 12%. It's very complicated. Okay, and I will explain why it's very complicated when we go to the third module. The 8% is basically the practical maximum that we construct, and typically it's within the 5%. Okay, the side friction factor, it's basically the coefficient of side friction FL. That's we can get it from this highway capacity curve. Okay, as you can see, you know, the higher the speed, the lower the side friction becomes. Any questions so far? Okay, I'm gonna stop here and we continue, inshallah, next lecture. Thank you.
Thank you, Doctor.